And then we have broader wavelength coverage. And so we'll be able to go from these kind of orders of magnitude constraints on, say, something like the metallicity in the atmosphere. I took out the whole water thing right here. I'm just going straight to metallicity. And say the abundance of carbon to oxygen in the atmosphere. We'll be able to go from orders of magnitude constraints to kind of factors of a few. And then we'll be able to address these science questions in more detail. Instead of having error bars that are this big on this plot, we'll have presumably error bars that are smaller on this figure. We'll be able to more cleanly separate water abundances that would be consistent with, say, high carbon to oxygen ratio versus low carbon to oxygen ratio compared to, say, what we're able to do now. We'll have much higher positions on these things. What I think is really going to happen is we're going to take our models, and none of them are actually going to fit the data well. And so then we're going to have to go back to the drawing board because planets are hard, right? We don't, this is kind of a sidebar, but we don't really have like a theory of planetary atmospheres, right? We can't just a priori predict that this planet's going to look like this one's going to look like this. We can all go home. It's not like we have our 8-parameter cosmological model that like we keep getting more data for. We have a bunch of models we don't know, and we don't know if they're going to work out. So it's still very much in a kind of a data-driven regime. So James Webb is going to solve some of our problems. I know some may disagree with this, but right at the end of the day, James Webb, as we've seen, it's been delayed, and it's also going to have a limit of life, highly competitive. I don't think the cosmologists and the stellar astrophysicists want us exoplanet people having all of the James Webb time. I'm sure there would be a revolt. So that leaves us kind of with a relatively small number of objects. We're not going to get thousands of objects. We're not going to be able to characterize the atmosphere of thousands of objects with James Webb, right? We're maybe going to be able to do these hot Jupiters. Maybe we'll be able to do on the order of 100 of those, but if we kind of mix that with terrestrial planets that we might want to characterize, right? People are really excited about characterizing terrestrial planets. That's going to reduce the amount of time we have to do sort of the statistical atmosphere, exoplanetology kind of stuff. So moral of the story here, James Webb is going to be great. We're going to learn a lot about the planets we observe, but we're not going to be able to observe all of the planets we want to. And even more gloomy, you can imagine that maybe the who knows what the fate of future flagship missions may be. And these are the types of telescopes that we would need to characterize the things that we want. But it's kind of up in the air. Are we going to get another $10 billion mission in the future? Right? It's kind of out of our control in a way. So we need to look to alternatives, right? So this is where I'm actually getting to my talk. Alternatives. So I want to talk about this. It's not really a new technique, but it's becoming more popular here. This high resolution spectroscopy. And what's nice about this is you can do it from the ground. Okay. So beyond just saying, oh, this is something we can do from the ground, there's also additional science enabled by looking at the spectra of exoplanet atmospheres at high resolution. Obviously, high resolution is better, right? There's more information there. So sort of one of the key advantages of looking at an atmosphere at high resolution, well, one, the molecules are less confusing, right? You can more cleanly separate which molecule is which. And so in that sense, you would have less degeneracy whether or not a molecule is there. And so going to high resolution is really good for detecting the presence of particular molecules. In fact, it was this high resolution spectroscopy from the ground was the first approach to detect a carbon-based molecule, CO, in the atmosphere of an extrasolar planet. So that was done in 2010. Carbon-based molecule. And so just to compare, a lot of what we've been doing right now with this high resolution approach, right? Usually, because of the way spectrographs are set up, it's hard to get a broad wavelength coverage. So you get a narrow wavelength kind of region on your overall kind of broadband spectrum here. Just think of this as flux and wavelength. But you get it at much higher resolution. And so also because you're probing higher resolution, there's kind of more dynamic range in the optical depths that you're probing in the atmosphere, so you can get a broader range of pressures that you're probing. So you can say more information about what's happening in the upper atmosphere, the thermal structure. I don't mean ionosphere or thermosphere. I mean kind of like stratospheric regions of the atmosphere where we might have these inversions. You'll have more information as you go towards high resolution.
How do you remove the Earth?
There. Okay, so this is how we remove the Earth. So how do we do this? We're looking through Earth's atmosphere, right? Earth's atmosphere is obnoxious, okay? There are far more, there's more expertise in the room on how to remove Earth's atmosphere, so this is my like crude modeler kind of explanation for it. So when you take a high resolution spectrum of an exoplanet or a star from the Earth, you're measuring Earth's spectrum. You just see Earth's spectrum, okay? Right? So you just measure a bunch of garbage. And so what you have to do is you have to fit this out. So there's detrending algorithms, and I'll talk a little bit more in detail about why this technique works. But if you detrend the Earth's atmospheric spectrum, you're left with noise, right? So this is relative planet to stellar flux, and then wavelength down here over a really narrow wavelength range. So this would be the K band. And so the actual planetary spectrum would be this little red line. And so these are little baby absorption lines that you would have in this atmosphere compared to this huge noise, okay? So, like, well, what the hell? So the solution here, right, is that how do I get anything out of this? The fact that there's a large number of lines right here, the fact that the signal to noise on any given line is really awful, right? It's like the noise to signal is like 10,000. And so what you do is you leverage the fact there's a large number of lines that are present at high resolution. And so that can build up the signal to noise of that molecule, right? A molecule isn't just one line or one band. It's many lines and many bands. So if you can measure many lines and many bands, you can boost the detectability of a given molecule. So I'm going to refer to this approach as high resolution cross correlation spectroscopy. That's a mouthful, so there's the acronym for it. Okay, so continuing on to your question, how does this work? So the basic idea, right, when I say detrending, so the planet is going in an orbit. That's what planets do. And so the planet has some Keplerian velocity around the star, and the star and planet system have some systemic velocity to us or away from us. Okay, and so that's going to impart a Doppler shift on the planetary spectrum. Okay, so if we take this black curve, let's say this is the true spectrum. Say the planet is here, and we're observing the spectrum at this velocity, and let's say we know what that velocity is because we're good at doing orbits, and we have, say, some radial velocity data on what the orbit actually is. And so let's pretend that we measure this black spectrum, but it gets all garbled from Earth's atmosphere and doing this telluric subtraction. How do we leverage the fact there's a large number of lines? Well, we use this technique called cross-correlation, where if you take some template spectrum, which would come from a model atmosphere, which has the knobs that we want to know, abundances and temperatures, we can Doppler shift that spectrum. So if we take a spectrum that, say, has the right molecules in it, if we take a model spectrum that has the right molecules in it, and we cross-correlate that with the black spectrum, you see that when we're at the right Doppler shift, when we're at the right velocity, these two curves are well correlated. They have a correlation coefficient of 1. This is just Pearson's correlation coefficient right here. But if we took a template that had the wrong molecules in it, and we were to Doppler shift that spectrum and try and cross-correlate it with the observed spectrum, we wouldn't get a strong correlation coefficient. So that would be this blue curve right here. So we would say that the red model right here is a better model than the blue model right here in cross-correlation speed. Okay? So we're leveraging, what we're doing is we're leveraging the motion of the planet as it's going around this star. Oh gosh, I'm so not going to get through everything. So why this works, why we can subtract out Earth's atmosphere. So if you plot wavelength right here and phase, so orbital position right here, as the planet is moving, so these are the different lines in the planetary atmosphere, these white streaks, so think of this as flux right here. Those kind of move around in wavelength as they're Doppler shifting sinusoidally. And so these black lines, as a function of time, those are Earth's telluric lines. Those don't change as a function of time. And so you can imagine dividing out in this direction, and you won't contaminate the lines, kind of the path of the planet lines as they're kind of moving in this direction. So you can actually, you're leveraging the fact that the planet is going in an orbit and that it's moving and that the velocity is changing rapidly for the planet, whereas the Earth's atmospheric lines are stationary. And so that's what allows you to divide out Earth's atmosphere without contaminating too much planetary signal. But the main consequence of this is through that approach of dividing out the tellurics, you completely delete any continuum information that you have of the planetary spectrum. So you don't have an absolute flux level. You just have lines, but you don't know what the continuum is, and you don't know what the slope of the continuum might be. So the challenge is, how do we extract atmospheric information in that regime? So I'm going to have to blow through this stuff really fast if I want to tell you what is really exciting. But the way people have been doing this so far is you take a template model spectrum, which comes from, say, a radio transfer model, and you go through that cross-correlation technique, and you kind of wiggle around what you think the planetary circular velocity is, and what you think the velocity is of the planet going, the planet-star system moving towards or away from us. And if you move those velocities around, and if we know what those velocities actually are, because we have external data, orbital information about the planet, you can make these what are called detection maps, where this would be the Keplerian velocity of the planet, and then the velocity to and away from us of the star-planet system. And when we have a good correlation, we would have this red blob right here. And so we say that we detected the atmosphere if we have a red blob, a high detection significance, at the location where we expect these lines to be Doppler shifted, okay? And so this is after going through all this telluric subtraction technique and doing this cross-correlation stuff. So if you see a red blob in these velocity versus velocity plots, that's telling you you're detecting your planetary atmosphere. So these are some of the earlier and more recent results. We've been doing this a lot lately with a variety of instruments and telescopes. I'm not going to talk about all of them. So like I mentioned, the first detection of CO came from using this technique. So you kind of see a strong, well, this is not very strong, but at the orbital velocity you expect, you detect kind of a non-negligible cross-correlation coefficient. This approach, here's this red blob here. This is a several sigma detection of TIO in an atmosphere. We can detect these blobs in non-transiting planets. And then recently we've detected